Hello everyone, welcome back to Deeksha Karnataka YouTube channel and in Brahmastra 2.0. Today I am going to discuss a medium important chapter, Electromagnetic Induction. In level of difficulty, this is a easier level, easier chapter, and if you practice few of the questions from this chapter, then definitely you can answer the questions that is going to be coming from this chapter. Also, we have completed a lot of chapters in this series, so if you have not watched those lectures, please go and check them out. All the lectures are going to be super duper important for all of you, right? So I am going to discuss, this will again be a very short duration lecture, not a huge 1 hour or 1.5 hour lecture. It will be less than 1 hour lecture, so don't go anywhere. Please go through the lecture, and if you are interested what is the blueprint of this chapter, so blueprint of this chapter, two questions will come as 1 marker, so that means we can expect one MCQ question and one fill in the blanks question. So both type of question will definitely come from this chapter, as well as we also have a 2 marker question and 3 marker question. So total marks allotted for this chapter is 7. Okay, now one important part from this chapter is that sometimes there is a possibility that a 2 marker numerical or a 3 marker easy numerical, all of the numericals coming from this chapter are easy and formula based. So there is a small possibility that you might face a question based on numerical based question from this chapter. Okay, but other questions are again important. So what are all the questions we are going to discuss? We are going to discuss 15 MCQs as usual. We are also going to discuss 5 fill in the blanks, 5 2 marker question and 5 3 marker questions. So total 30 questions I am going to discuss in very quick time. So let's start with the first question. The energy stored in an inductor of inductance capital L in establishing the current in it is. So what is the energy stored in an inductor? Energy stored, work done is same, both are given by half Li square. So correct answer is half Li square. So option D is correct answer. Okay, so this same question might be coming as what is the work done to establish a current in an inductor? What is the work done to establish a current in a conductor? What is the energy stored in an inductor? Everything will have the same formula, half Li square. Now the following are the statements related to self-inductance. So there are 2 questions related to self-inductance. The self-inductance of a coil depends on its geometry and on the permeability of the medium inside it. Second point says that the self-inductance is a measure of electrical inertia and opposes the change in the current in the coil. Now self-inductance depends on the mu naught or mu, that is permeability of the medium. It also depends on its area, depends on its length. So this statement is a true statement. This is also a true statement, okay, because self-inductance acts like inertia. Now if you forget what is inertia, suppose you are at rest. Okay, I am asking you, please go and study. So what is your inner motion is saying? Sir, ignore sir, I don't want to study right now. So basically it's like the inertia of your initial inertia which is stopping you from being studying. So if you are studying right now and if you are very deeply into the studies and someone asks you, hey, can you come and do something for me, then you will say, no, I am studying, I don't want to go right now. So that is another inertia. Okay, that is a good inertia, one is bad inertia. So there are also inertias of motion, inertias of rest. So when the object is at rest, it does not want to move, it wants to stay at the state of rest. Similarly, if an object is moving, it always wants to stay in the state of motion and it does not want to stop. So these are the 2 types of inertia that we have learned in mechanics. Now electrical inertia means when electron is trying to flow through a conductor, okay, initially it does not want to go through that motion, and that stopping, whatever is stopping that is actually the self-inductance. Okay, and self-inductance acts, that's why it is called self-inductance, acts like electrical inertia. So it's trying to stop the current. Okay, so that is why the second statement is also correct. Okay, both statements are correct. Both statements are correct, so option C is correct for this question. Now next question, magnetic flux is a scalar quantity and its SI unit is Weber. Okay, magnetic flux is a scalar quantity and its unit is Weber. So correct answer is this, option B. Okay, now next, before continue, I just want to remind you, if you are watching our channel for the first time, don't forget to subscribe to our channel, share this video with your friends so that they can also learn and understand the important questions for your PU boards and also prepare well, right? You also want to help your friend, right? Don't be selfish, help your friends as well. Also join the WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. There you will get all the class notes, all the important updates, news, etc., right? So don't forget to, two things you have to do. First of all, subscribe to our channel, and secondly, join the WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. If you are watching this from your mobile, you just click on this link and you will be directed to the channel, and you can join or follow the channel. Basically, then you will get every update in our channel, right? Now let's move on to the next question. This is actually a two question. Instead of giving them separately, I have given them in one question because options are same. The polarity of induced EMF in a coil is given by dash. Okay, or another version of the question, which of the following is a consequence of conservation of energy? Both questions have same answer, and you guessed it correctly. It's Lenz's law or Lenz's law. Okay, whatever you say it, Lenz's law, Lenz's law. Okay, so that determines the polarity of the induced coil. Also, it is the consequence of conservation of energy. We will see that in a while in a descriptive question, how it is related to conservation of energy. So that's this is the question. Both questions have came in the past and might come in the future as well. Just you need to remember what is the language and answer. Next question. Current in a coil changes from 1.6 ampere to 0.2 ampere in 2 seconds, inducing an EMF of 2.8 volt. The value of self-inductance of the coil is. So they asked you what is the self-inductance of a coil. We know that in case of self-induced coil, the induced EMF is given by the self-inductance into di upon dt, change in current. Okay, so similar to that of normally, if the induced EMF is given by n d phi by dt, right? From Faraday's law, there is a negative sign, but this is the normal expression for the magnitude, right? Here they asked you that again there is a negative sign here as well, but because current is decreasing, we can ignore the negative sign. But current decreases from 1.6 ampere to 0.2 ampere. So what is the change in current? Change in current is given by 1.6 minus 0.2. So it was initial value, it changed to 0.2. So the change is 1.4. Okay, so this is the change in current. Change in current is basically difference between two currents. Okay, 1.4 is the change in current. Now what is the time given over here? Time given is 2 seconds. So if you divide it by dt, it will be 2 seconds and you will get 0.7. Okay, so 0.7 is the value of di by dt, and induced EMF is given by 2.8. so just put the values. So 2.8 is the induced EMF, L is unknown, and di by dt is 0.7. so L is equal to 2.8 divided by 0.7, that is 4. Okay, so correct answer is 4 Henry. Correct answer 4 Henry. Okay, next question. The dimensions of inductance is. So dimension of inductance is, how to calculate this? So for that we will use a basic rule that energy, okay, energy stored in an inductor is given by half Li square, right? We already discussed it in one of the MCQs that energy stored, work done, etc. is given by the same formula, which is half Li square. Now, it is very difficult for us to understand what is the dimension of inductance if we start from any other formula. This is the easiest formula to start with. Why? Because energy is same as that we learned in our mechanics. Now, what was the energy formula? If you remember, energy or work done, that was given by force into displacement, and there was a cos theta, but if they are in the same direction, theta is cos theta is 1, so fx. Okay, what is the dimension for F? This is the one dimension that you have to remember, there is no other way. What is the dimension of force? Dimension of force is m L t to the power of minus 2, mass into acceleration. Okay, m L t to the power of 2 is the dimension of force. What is the dimension of x? X is nothing but length, so you multiply them, so m L t to the power of minus 2 into L, that means the dimension of Fx or energy is given by ml square t to the power of minus 2. This is the easy dimension. You can remember this dimension, or you can formulate what is the dimension of energy. Now that dimension we know. So dimension of energy is m L square t to the power of minus 2 equals to, this half is dimensionless, so dimension of L and dimension of current. So what is the dimension of current? Dimension of current is known, it is A, so A square, right? I square is there, so that means dimension will be A square. Now you can find the dimension of L. So dimension of L is given by m L square t to the power of minus 2 a to the power of minus 2. This a comes to other side and becomes to the power minus 2. Okay, so the correct answer is m L square t to the power minus 2 a to the power minus 2. Option A is correct. Okay, this question is one of given in one of your model question paper. So if you are wondering, sir, why you should do the difficult question, this is given in your model paper, so you have to do it. Now next question. Which of the following quantity is measured in Weber per ampere? So Weber per ampere, what is Weber? Weber is magnetic flux. Weber is magnetic flux. Okay, and you are trying to find what is Weber per ampere. So Weber per ampere means if you divide flux with current, you get self-inductance. You get self-inductance. This is nothing but self-inductance. So self-inductance is the unit of Weber per ampere, also called Henry. Okay, Weber per ampere and Henry are same. An AC generator is a device used to convert electrical energy into mechanical energy. Device used to convert mechanical energy to electrical energy, both A and B, none of the above. So AC generator is something which generates AC. Okay, generates AC means what is AC? AC is a alternating current. AC means alternating current, right? So basically AC generator is generating alternating current, that's why it is called AC generator. Okay, and generation means it has to generate from somewhere. So what form we are using? We generally use rotational motion of turbine to generate electric current. So basically it's a device used to convert mechanical energy into electrical energy. So all the places where you have heard that hydroelectric power plant, coal power plant or windmill, they all are basically an AC generator, okay, which is generating AC by using some other form of energy, mainly mechanical energy. Okay, even if you are using hydroelectric power plant where you are using energy stored in water, basically the energy stored in water is basically the mechanical energy. That mechanical energy is given into a rotator turbine. That turbine rotates at the high speed, and because of that the power is getting generated. Okay, that is the major principle. Okay, except solar power plant. Solar power plant can directly convert energy, solar energy into electrical energy. Okay, where we use solar cell. Other than that, all the forms of energy are basically coming from our AC generator, and AC generator always converts mechanical energy to electrical energy. The SI unit of mutual inductance, Henry, okay, or Weber per ampere, both are same, so Henry is the answer. The expression for motional EMF is BVL or BLV. Okay, so this is the expression for motional EMF. Next, the magnetic flux through a surface of area A placed in an uniform magnetic field B is defined as, so magnetic flux is defined as phi equals to B dot A. Phi equals to B dot A. So this is the magnetic flux, so this is the correct answer. Next, to induce EMF in a coil, the magnetic flux linking must remain constant, must increase, must decrease, both B and C. It can increase or it can decrease, both is possible as long as it is changing. There will be an EMF induced linked with the coil. Okay, so as long as magnetic flux changes with time, with respect to time, okay, there will be an induced EMF. So both B and C is correct. If it is increasing, the current direction of current in a particular direction. If it is decreasing, the direction of current in the opposite direction. So only the direction of current will change, but as long as it changes, okay, as long as magnetic flux linked with the coil changes, there will be an induced EMF. Next question. When a magnet is moved with its north pole towards a closed coil, the nearer end of the coil acts as. So here is a coil and you are moving a north pole towards the coil, okay, towards the coil. So the north pole is moving towards the coil. That means this near end of the coil must produce another north pole so that it tries to stop the motion. That is the Lenz's law. Lenz's law says that the direction of current is such that it tries to stop or oppose the cause of the motion. So cause of the motion is the motion of the north pole. So that's why it will produce a north pole in the side of the coil facing the magnet. Okay, so the nearer end of the coil will be a north pole. So correct answer option A. Next question. The magnetic flux linked with the coil varies as phi equals to 2t square plus 2t. What is the magnitude of induced EMF at t equals to 0.5 second? So phi is given as 2t square plus 2t. So induced EMF is d phi by dt at t equals to 0.5. So that is 4t plus 2, and we have to put the value of t as 0.5. So 0.5 into 4 is 2. So 2 plus 2, that is 4 volt. Okay, I think the options are given here in wrong. So correct answer will be 4 volt. So 1 volt, 2 volt, 3 volt, 4 volt. So correct answer will be 4 volt, option D. Next, the SI unit of magnetic flux is, the SI unit of magnetic flux is Weber per meter, Tesla per meter square, Weber per meter square. So again it's Weber, again it is from your model question paper. They have directly asked what is the SI unit. Okay, in one of our previous question it was asked whether it is a scalar quantity or vector quantity. So it's a scalar and unit is Weber. Now next, now you have to solve fill in the blanks question. The device which works on the principle of electromagnetic induction is. So which of the device works in the principle of electromagnetic induction? Let's see. Magnetic potential energy, is it a device? It's not a device. Conservation of energy, is it a device? Not a device. Inertia, is it a device? Not a device. AC generator, is it a device? Yes, it is a device. Is there any other device mentioned here? Allows and opposes. Allows and opposes again are not a device. So only AC generator is a device. So it's an easy answer. Even if we don't know, we can guess the answer. It is AC generator. Lenz's law is based on conservation of energy. Okay, it's based on conservation of energy or consequence of conservation of energy. So we also know the second answer. Self-inductance plays the role of electrical inertia or normal inertia. Okay, so basically self-inductance plays the role of electrical inertia is more accurate, but inertia is also fine. The energy stored in a inductor, energy stored in an inductor in the form of, so energy stored in a inductor is in the form of magnetic potential energy. It is called magnetic potential energy. So from the option we can see that magnetic potential energy is the correct answer. induced EMF always dash any change in the magnetic flux. So again, this is a statement of Lenz's law, which says that it always opposes any change in the magnetic flux. So correct answer is opposes. Okay, so this is opposes. Okay, so fill in the blanks are also done. Now let's move into the 2 markers category. Give the principle of AC generator. Why is a current induced in an AC generator called alternating current? Very interesting. Mention the expression for induced EMF in it. Okay, so either this question will come, give the principle of AC generator, why the current induced in an AC generator called alternating current, or give the principle of working of AC generator, mention the expression of induced EMF in it. So this is actually a 2-mark question when principle and expression or principle and why it is called AC, this question will come. All three questions generally will not come. If all the 3 are coming, then it will be a 3-marker question. Now, what is the principle? An AC generator converts mechanical energy into electrical energy by changing the flux linked with this rotating coil. So here is a rotating coil, and as it is rotating, the flux linked with the coil changes, and that's why there is an induced EMF. And induced EMF means it produces current as well, because EMF is the source of current, it's a parent of current. Okay, the direction of the current produced in an AC generator changes periodically. Okay, so the direction of current produced in an AC changes periodically, and therefore the current is called alternating current. Normally the current that we have used so far in our current electricity chapter was a DC current, direct current. Direct current means, suppose this is the value of voltage, okay, and this is time. So DC current means it does not change its direction, it remains same. But when you talk about AC current, okay, so what happens in this case is that if you are considering the voltage, okay, the voltage alters every now and then. Okay, there is a fixed time interval after which the direction of the current changes, and as you move on the with time, okay, after each and every time it will change its direction, and that's why it is called AC. So this is an example of AC current. Okay, the voltage value changes, plus and minus, whereas in direct current the direction of current remains same. Okay, the expression for induced EMF in a AC generator is given by NBAW omega T. Now if this question is asked, you have to mention what is N. N is the total number of turn, what is B? B is the magnetic field, what is A is area, and what is omega? Omega is angular speed. Right, so you have to mention these terms as well to get the full marks. Now, next question. State Faraday's law and Lenz's law of electromagnetic induction. Okay, Faraday's law, the time rate of change of magnetic flux through a circuit induces EMF in it, and Lenz's law, this came only once, most of the time it came was Lenz's law. Okay, the polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produced it, and it is basically minus d phi by dt. So this negative sign comes from Lenz's law, and this d phi dt comes from Faraday's law. D phi dt is due to Faraday's law, and minus sign comes from Lenz's law. Mention any 2 factors on which the self-inductance of the coil depends. So self-inductance formula is given by mu naught n square A into L. Self-inductance is directly proportional to the square of the number of turns per unit length. Self-inductance directly proportional to the cross-sectional area A of the solenoid. Self-inductance is directly proportional to the length of the coil. In fact, if you take most general expression, then instead of having mu naught, it will be mu. Okay, so L will be mu n square AL. Okay, so in that case, even you can mention that self-inductance is directly proportional to the permeability of the medium. That is also true. Okay, so here we have only taken n square, a and l. Now 2 factor means any 2 will be fine. If they ask you 3 factors, that's why you have to remember all the factors, and if you remember the formula, that will be very, very helpful to write this question, answer this question. Okay, so that's why I have given 3 options, even though it's mentioned in 2 marker, even though 2 options are given in this question. But if the same question is asked as a 3 marker, then also you should know how to write it. Okay, now next question, calculate the magnetic energy stored in a coil of self-inductance 0.05 Henry carrying a current of 0.2 ampere. This is again taken from your model question paper. Okay, so let's see. So energy is given by U equals to half L I square. Okay, so the value of L is given here 0.05 and current is given as 0.2. Just put the values, use your calculator and calculate it. Okay, half 0.05 into 0.2 into 0.2. So it will cancel, you get 0.1, or you get 0.2 into 0.05 is 0.01 into 0.1, that is 0.001 joules. SI unit of work done, energy is joules, so correct answer is 0.001 joules, and if you solve it, you will get full marks, full 2 marks. Simple answer, nothing to worry, even you can use your simple calculator to calculate it. Now next question. An aircraft with wingspan of 40 meter flies with a speed of 300 meter per second in eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the Earth's magnetic field is 1.75 into 10 to the power of minus 5 Tesla. Calculate the EMF developed between the tips of the wing. So this is, there is a plane which is flying. Okay, the wingspan is given. Okay, it is flying from west to west or west to east? Eastward. It is flying eastward. So it is flying in eastward direction, and the vertical component of magnetic field is given over here. Okay, and they are asking what is the EMF induced between the wingspan of the plane. So that means we will be using a simple formula. Whenever there is a motion of an object in a magnetic field, there is an induced EMF, and that is given by BVL. Okay, what is B? B is given over here, so no need to worry, everything is given. 1.75 into 10 to the power of minus 5. Velocity is given 300 and L is given as 40 meter. So if you multiply everything, it will be simple problem. 4 into 1.75, 2, 6, 3 and 4, 7. So 1 into 1.75. So 1.75 is 5, 6, 7 by 4. Okay, so 1.75 is 7 by 4. So 7 by 4 into 10 to the power of 5 into 300 into 40. So this cancels and we get 10 over here, 10 over here. So 3 7s are 21 and 1 2 3 zeros are here, so it will be 10 to the power of minus 2 or 0.21 volt. So you will get 0.21 volt as induced EMF. Now next, derive the expression for motional EMF induced in a straight conductor moving perpendicular to uniform magnetic field. So first of all, you have to draw this diagram and show the magnetic field is either out of the paper or into the paper. Here we have taken the magnetic field into the paper. So into the paper means cross, out of the paper means dot. Okay, so this is the basic meaning. The cross means this is your target, so that means it is going into the paper. Dot means it is coming out. Okay, Okay, so this is how it should look. Now what you have to do, you have to take the velocity of the rod which is moving is given by v. This is x and this is L. Okay, this length is L. So this length is L, this distance is x. Now we have to apply Faraday's law and we have to calculate the induced EMF. Faraday's law as well as Lenz's law, both law you will apply. So first of all, what is the flux linked with this coil? So flux linked is given by, magnetic flux linked with the coil is given by the magnetic field times area. Okay, cos theta, in this case theta is equals to 0 degree, so that's why it is only BA. Okay, perpendicular, in the case of perpendicular theta becomes 0 degree, so it is B dot A. Now phi is given. Now what we have to calculate is what is area A over here. So this is a rectangular frame, right? So rectangular frame means area is length into breadth. Length into breadth is the area. So flux linked with the coil is given by B into length into breadth, that is L into x. So phi we know. Now you have to calculate the induced EMF. What is the formula for induced EMF? Induced EMF is given by minus d phi by dt. Right, why minus? Because of Lenz's law there is a negative sign. So we have to differentiate it with respect to the speed. So we get epsilon equals to B into L into dx by dt. So when we differentiate this, B is constant, the length is also constant, only thing which is changing is this x. As it is moving over towards this side, okay, the x value is changing, and x value is not only changing, it is decreasing. Okay, so x value is decreasing. So from there we can say that velocity of this rod is given by minus dx by dt. Now why this is negative sign? Because x is decreasing with time. X is decreasing with time, that's why velocity is given by minus dx by dt. So therefore we can write epsilon equals to BLV. Okay, so this is the expression for induced EMF in a coil. This is the expression for induced EMF in a coil. Now next, describe an experiment to demonstrate the phenomenon of electromagnetic induction using a bar magnet and a coil. So this is the bar magnet and coil experiment. This question has came in the past and also given in your model question paper in a different form. So that's why I thought this question, and if you are preparing for preparatory, this question is a common question which is coming in preparatory from many previous years. So let's see. So here first of all you have to draw this diagram where you have to show the coil and a magnet. The magnetic field lines, you have to clearly show these magnetic field lines, and there is a galvanometer which is deflecting. Okay, so when the magnet approaches the coil, and if you can describe the image by one line, okay, otherwise this is sufficient answer. When the magnet approaches the coil, the galvanometer needle deflects, indicating a current is induced. When the magnet is pulled away, the needle deflects in the opposite direction, showing that the current reverses. No current is induced when the magnet is stationary relative to the coil. So these are all the observations. Okay, so when you are taking the magnet towards the coil, there is a deflection observed in the galvanometer. When you pulling the magnet away from the coil, okay, the deflection is in the opposite direction. That means the current induces in the opposite direction. And if the magnet is not moving, no current is induced, that means total induction is 0. Conclusion. So this is the explanation part. Okay, this experiment demonstrates the electromagnetic induction. A current is induced in the coil when the magnetic flux through the coil changes. This confirms Faraday's law of induction, and the direction of the current follows Lenz's law opposing the change in the magnetic flux. So these are the 2 points that you have to remember. Not super difficult, easy to explain. You don't need to write the entire detail of the experiment. This is the main crux of the experiment. That is what you have to write, core of the experiment. You should not skip anything in there. Okay, but the diagram is compulsory if they ask you magnet coil experiment. Now next question, a horizontal straight wire 10 meter long is falling with a speed of 5 meter per second at right angles to a magnetic field of 0.3 into 10 to the power of minus 4 Tesla. Find the instantaneous value of the EMF induced in the coil. Again, the formula for this is also same, that is BVL. So sometimes the same problem can be asked as a 2 marker, sometimes the same problem can be asked as a 3 marker. Does not matter, as long as you can answer them, as long as you can solve them, and the formulas are very simple, straightforward, and you should get marks if you answer it. Okay, speed falling with the speed is 5 meters. So don't pay too much attention into the problem. You just need to think that the formula, only one formula which will fit for this problem is this BVL. So just put that. Length is given 10 meter. Okay, so it will be 3 5s are 0.3 into 5 is 1.5 into 10 to the power of minus 3 volt. Okay, so 1.5 millivolt or 1.5 into 10 to the power of minus 3 volt. So this is the correct answer. Okay, 1.5 millivolt. Okay, or 15 into 10 to the power of minus 4 volt. Any one form is correct. Okay, so I thought this might be the correct approach. Any one answer is, as long as the 10 to the power value is correct, you will get full marks. Lenz's law is the consequence of law of conservation of energy. Explain. This is the question I was talking about during the fill in the blanks. When a changing magnetic field induces a current in a conductor, the current creates its own magnetic field. According to Lenz's law, this new magnetic field opposes the change that caused it. So first of all, let us understand this. This is a very important point. So we know that whenever a current is passed through a conductor, it produces a magnetic field. It can be, if it is a straight wire, we know the formula. If it is a current carrying circular coil, we know the formula. Okay, in the previous chapter we have learned that whenever a current is passed through a conductor, it produces a magnetic field, right? So current and conductor is needed to produce a magnetic field. Now in this chapter, what we are dealing with, we are changing some external magnetic field, and that changing magnetic field is producing an induced current, right? So whenever a current is we are trying to produce a current, okay, for that what we are doing, we are adding some external magnetic field into the picture. So first, this case, no external magnetic field is there, only current in a coil, and current produces magnetic field. Now we have reversed the idea. We are adding some external magnetic field, and that magnetic field is now producing the current. Coil magnet experiment. Okay, in the coil magnet experiment we did that, where we had a coil, we had a circuit, and we say if we can change the magnetic field linked with the coil, okay, it produces a magnetic field, right? So this is how this works. Now magnetic field producing current, but basic property of current in a conductor is that it will also produce its own field, right? So this magnetic field is producing the current, right? But the current on its own right can also produce magnetic field. So what will happen, what should be the relationship between these two magnetic fields? Okay, one magnetic field is the original magnetic field which is responsible for creating the current. The current is also producing the magnetic field which is basically in response of the original magnetic field. So this is called induced magnetic field, and this induced magnetic field will oppose the cause. So suppose a north pole is moving towards it, then there will also be a north pole which will be produced in this end of the coil, so that they repel each other. That is basically Lenz's law. So Lenz's law is basically talking that if there is a magnet which is approaching a coil, whatever surface which is facing the magnet, the pole which is induced will be opposite. That's it. Now let us understand with explanation. If the induced current did not oppose the change, suppose instead of opposing it, it supports it. Suppose Okay, we are just taking a hypothetical case where this is a south pole. Okay, so it would create a runaway situation where the system gains energy without any input. So what is the meaning of that? Suppose a south pole is created over here, a north pole is already there. Now you are trying to push the magnet. Now what happens, this south pole, after some time, when you are pushing the magnet towards the coil, after some time this south pole will be strong enough so that it can attract the magnet towards it. Okay, so it will be strong enough to pull the magnet towards it. So you don't need to do any work. The magnet will automatically move towards the coil. It will go away and again it will come back. So like automatically the magnet will start oscillating and you will start producing current without doing anything. So if that was possible, then electricity would have been absolutely free of cost. There would be no charge, nothing. You don't need to pay anything, and you can produce energy out of nothing, which is prohibited by conservation of energy. Okay, so you to produce energy you have to spend some energy, right? That is the conservation of energy. Okay, so that this effect is called a runaway effect. So automatically energy is getting produced without doing anything is called runaway effect. Okay, where the system gains energy without any input, violating the law of conservation of energy. For example, if you move a magnet towards the coil, the induced current generates a magnetic field that repels the magnet. You must do extra work to push the magnet closer to the coil, and this work is converted into electrical energy. Thus, no energy is lost or created. It is transformed from mechanical energy to electrical energy. So, because you are pushing, when you are pushing the north pole, and because there is a north pole which is being produced over here, you have to do some mechanical work to keep on pushing the magnet. So when you are pushing the magnet towards the coil, okay, you have to keep on pushing it so that it is not an automatic effect. You have to do some external work to produce that energy. Okay, so this is why, this is a consequence of conservation of energy principle, and Lenz's law also coming from the fact that it is a law of conservation of energy. So this is a new question, might be asked in your paper, so be prepared for this question. Now, derive the expression for magnetic energy stored in a coil. This is from your model paper, last question of the day. Prove U is equal to half Li square. Okay, now how to do that? First of all, suppose we have a coil and you have established some EMF around this coil by doing some external work. Say the EMF is epsilon. Okay, the self induction is L. The current that is flowing in this is given by I. Okay, so you developed some back EMF which is given by epsilon. So what is the work that you have done to establish this current? That is very, very important. The work that you do to establish this current is given by dW by dt equals to epsilon into I. Okay, epsilon into I. So you remember that the work done or heat developed in a circuit was given by VIT in electrical circuit. Okay, so that is equivalent to work done. So if you consider H by T, then it will be V into I. So in this case, V is nothing but EMF, current is I. Okay, so this is exactly what we know. Okay, so but the form is slightly different. Instead of heat energy, we are considering work done. Okay, work done and energy are related. So from that fact, if you forget it, the work done per unit time is given by induced EMF into current. Okay, induced EMF into current is the work done. Now what, this induced EMF in a coil of self inductance L is given by L di by dt. Only we are taking magnitude. Okay, if you consider negative sign, then there will be a negative sign, but we are not using that. We are only using the positive sign. Okay, so epsilon is basically di by dt. So if you put that, you will get dw by dt equals to L di by dt into this I. Okay, Now this dt and dt can be cancelled, so we get dw equals to Li di. Now what is the total work done? Total work done is given by 0 to w. Initially work was 0, dw, that is equals to 0 to I. To establish the current from 0 to I, Li di. Now L is constant, so it will come out of integration. So you will get integral I di. What is the integration of I di? I di is similar to x dx. Okay, so what is the integration of x dx? X square by 2, right? Now 0 to I is the limit, so that does not change anything. So L into half I square. 0 to I you can put, and you will say that for 0 it becomes 0, only for I it left, so you get half Li square. Now here we have calculated the work done, but in the question they asked you the energy stored. From the definition we know that energy stored is basically work that you do, that is equals to half Li square. So this is the derivation, easy derivation, and if you do this you will get 3 marks. Okay, this is a new question from your model paper, and we have solved all the questions that is there in your model paper, as well as all the questions in previous year papers as well from this chapter. So I hope you enjoyed this session. I'll be back with a new chapter very soon. Till then, bye. But don't forget to subscribe to our channel and also join the WhatsApp channel. Link of the WhatsApp channel is given in our description.